In this season, we look at how it all works, the big ideas behind everything from the fabric of the cosmos to the networks that connect us. Welcome to Explain It to Me, the series where we break down the world's most fascinating concepts in plain language. Our mission? To take big, complex ideas, the kind that make you go, huh? And explain them in a way that makes you go, aha. Instead of dry jargon, we'll use real-world comparisons and a dash of humor to bring these ideas to life. Today, we look at Einstein's theory of relativity, a mind-bending idea that turned our understanding of space and time upside down. Don't worry, we'll keep it simple, with fun metaphors and real-life examples. By the end, you'll see why Einstein's relativity matters, from time-dilating space travels to the GPS in your phone. Let's unravel the universe, one easy analogy at a time. Einstein's first big insight, special relativity, basically says how you measure space and time depends on how you're moving. Imagine the universe as a giant highway with a strict rule. The speed of light, about 300,000 kilometers per s or 186,000 miles per s, is the ultimate cosmic speed limit. No matter how fast you go, you can't catch up to or exceed a beam of light. You'd need infinite energy to do so. In fact, light's speed is constant for everyone in every situation. Sounds simple, but this has some very weird effects. No absolute viewpoint. There's no single correct frame of reference. Motion is relative. Whether you're at rest or moving depends on who's watching. No universal stationary platform in the cosmos. A universal speed limit. Nothing with mass can go faster than light. If you keep accelerating toward light speed, nature says, nope. You'd require infinite energy to push any faster. And no matter how fast you chase a light beam, you'll always measure it racing away at 300,000 kilometers per s. Because the speed of light is unbreakable and constant, space and time flex to enforce that rule. Think of it like the universe's way of keeping things consistent. If you start moving really fast, time itself slows down for you, a strange effect called time dilation. It's not science fiction. A fast-moving clock literally ticks slower compared to one at rest. Distances shrink in your direction of travel, and even mass gets extra heavy from an outside perspective. Good thing you don't feel that. Reality warps just a bit to keep that light speed limit intact. To picture time dilation, imagine a pair of twins. One stays on Earth while the other zooms off in a rocket at near light speed. When rocket twin comes back, they'll be younger than the Earth twin less time passed for them. This is the famous twin paradox. In fact, NASA tested a version of this with real twins. Astronaut Scott Kelly spent nearly a year on the orbiting ISS while his twin Mark stayed on Earth. Scott's time ran slightly slower. He aged about 5 milliseconds less than Mark. Sorry, no dramatic fountain of youth effect at orbital speeds. 5 milliseconds is tiny. But if Scott could have zoomed at, say, 99.9% of light speed, the difference would be huge. For example, a 15-year-old who joyrides a spaceship near light speed for 5 years would return still a young adult of 20, but her classmates back home would be senior citizens around 65. Fast travel equals slow aging. Talk about a time warp. Another wild outcome is that simultaneity is relative. In everyday life, we assume two things can happen at the same time, absolutely. But Einstein showed that whether two events are simultaneous depends on your motion. For example, imagine two fireworks go off at the same moment, one in New York and one in London. To an observer on the ground, they might seem perfectly synchronized. Yet to someone flying in a plane between New York and London, one flash could appear to happen before the other. In relativity, there's no single universal now that everyone agrees on. Trippy, right? It's as if time has a personal touch. Your now may not match mine if we're moving differently. Don't worry. For everyday speeds like cars or planes, these differences are ridiculously tiny. You won't miss your Netflix show because of relativity. After special relativity, Einstein took things a step further with general relativity, which tackles gravity. Newton imagined gravity as an invisible force pulling objects. Einstein's genius twist: gravity isn't a force at all, but a feature of curved space and time. In his view, massive objects warp the fabric of space-time, kind of like a bowling ball on a trampoline stretching the surface. The result? Other objects move along curves in that warped space, and we feel that as gravity's pull. As physicist John Wheeler neatly summed it up, matter tells space how to curve, space tells matter how to move. So, according to general relativity, Earth orbits the sun not because the sun reaches out and yanks on Earth, but because the sun's mass curves spacetime and Earth is rolling along a curved path in that distorted space. Think of kids running in a park. If the ground were flat, they'd run straight. But if the ground is a hill that dips, they naturally loop around the hill. Similarly, planets loop around the sun's gravity dimple. Light itself can follow these curves. During a solar eclipse in 1919, astronomers observed starlight bending around the sun, just as Einstein predicted. It was like space was flexing in real time, proving gravity can make light rays take a detour. General relativity also says that time and gravity are linked. Clocks tick slower in stronger gravity. If you live at sea level, closer to Earth's massive bulk, time runs a smidge slower than it does on a mountaintop. Don't cancel your mountain vacation. The difference is incredibly small, but it's real. In extreme cases, like near a black hole, this effect becomes sci-fi crazy. A minute near a black hole might correspond to years elsewhere. Remember the movie Interstellar? The astronauts near a black hole experienced severe time dilation. That was real physics in action. Gravity not only bends space, it drags on time itself. You might be thinking, okay, cool weird science, but I'm not planning to ride a light-speed rocket or visit a black hole. Does relativity actually affect me? Absolutely yes. Einstein's theories show up in everyday tech and important applications. GPS and satellites. Every time you use Google Maps or your car's GPS, you're tapping into Einstein's relativity. GPS satellites carry precise atomic clocks. Because they whiz around Earth at 14,000 kilometers per h, special relativity makes their onboard clocks run about 7 microseconds slower per day than clocks on Earth. But here's the twist. Those satellites are also high above Earth where gravity is weaker, so general relativity makes their clocks tick 45 microseconds faster per day than ground clocks. Add those up, and without correction, a GPS satellite would get 38 microseconds ahead of Earth time each day. A few millionths of a second might not sound like much, but that timing error would translate to your GPS location drifting by kilometers enough to put you in the wrong town. Engineers program relativity into GPS so your navigation stays accurate. In short, your phone's map works because of Einstein. Electronics and magnetism. The device you're using to read this, be it a phone or computer, relies on electricity and magnetism, which are united by relativity. The fact that moving charges create magnetic fields and vice versa ties back to special relativity's rule that laws of physics are the same in any frame. Every transformer, electric generator, or MRI machine quietly owes a debt to Einstein's insights. So, when you charge your phone or use a credit card scanner, you're seeing a bit of relativity under the hood, even if it's not as obvious as a time-traveling twin. Golden glow of gold and more. Fun fact, the reason gold is yellowish and not silver-white like most metals? Relativity. The electrons in heavy gold atoms move fast enough, near light speed, that their masses increase and their orbits contract, altering how light is absorbed and giving gold its unique color. Similarly, mercury is liquid at room temp, partly thanks to relativistic effects in its atoms. Einstein's theory even explains quirks of matter in chemistry. In essence, relativity isn't just some esoteric theory for physicists. It's woven into the fabric of modern technology and natural phenomena. It taught us that time can stretch and space can bend, which revolutionized physics and enabled much of our high-tech world. It also unlocked cosmic mysteries. Without it, we wouldn't understand black holes, gravitational waves, or the expanding universe. Einstein's once crazy ideas turned out to describe reality more accurately than Newton's common sense version. So, what have we learned? Einstein's theory of relativity, special plus general, showed that space and time are not rigid separate things. They're a unified space-time that can flex like a rubber sheet. Speed affects how time flows, and mass shapes the geometry of the universe. We've explored how clocks on fast planes tick a bit slower, how your head ages slightly faster than your feet, because it's farther from Earth's gravity, and how a beam of light always outruns you no matter what. It's a wild universe where time is relative and gravity is geometry, yet we experience its consequences every day, from GPS to gold's shine. Not bad for a theory dreamt up by a patent clerk with a big imagination and even bigger hair. And that's it for today's Explain It to Me episode. We hope we untangled relativity in a way that clicked for you, and maybe gave you a laugh or two. Why does Einstein's theory matter? Because it literally changed how we see reality, and it makes possible some of the technology you use each day. Time and space will never feel quite so straightforward again, but that's part of the wonder of science. Reality is amazing once you explain it. Join us next time as we switch gears from the cosmic to the everyday and tackle another seemingly magical topic: how the internet works. Ever wonder how clicking a link sends information across the world in a blink? We'll break it down. Until then, stay curious and remember, even the craziest ideas might just be true in this incredible universe of ours.